So we are going to prove that the Euler's totient function is multiplicative, which is a very important property of the function, and we'll talk about what that means in a second. In order to do that, we're going to use something called the Chinese remainder theorem, which is another important theorem in number theory. So if you aren't familiar with that theorem, I've left a link to a playlist in the description that goes over what the Chinese remainder theorem is and a few examples. So you can watch those and then come back here. In order to understand what we're talking about with the Euler's totient function, let's look at the example of finding the totient function of 12. Now we know the totient function counts the number of integers between 1 and 12 that are coprime to 12. If we look at all of the integers between 1 and 12, which ones are coprime to 12? Well, we know that 12 is equal to 2 squared times 3. That's its prime factorization. So any numbers in here that have a factor of 2 or 3 will not be coprime to 12. So we're looking for numbers that don't have a 2 or 3 in their prime factorization. So these four numbers, 1, 5, 7, and 11, those are the numbers that are coprime to 12. And since there are 4 of them, the totient function of 12 is equal to 4. Now, we said that 12 is equal to 2 squared times 3. So I have another question, which is what is phi of 4, which is 2 squared, and what is phi of 3? Well, we know that phi of 4 is going to be all the integers in 1, 2, 3, 4, coprime to 4. Since 4 is 2 squared, that's all the odd numbers. So 1 and 3 share no factors with 4, and that means phi of 4 is 2. Similarly for phi of 3, we're looking at the set 1, 2, 3. So we want all the numbers in here that don't have a factor of 3. That's going to be 1 and 2, which means phi of 3 is equal to 2. Now there's something interesting happening. Notice, phi of 4 is 2, and phi of 3 is 2. If we multiply these, 2 times 2, we get 4, which is phi of 12. So phi of 4 times phi of 3 gives us phi of 12. That's a little bit odd because these numbers that we see up here, 1, 5, 7, and 11, don't seem like they're really related to these numbers down here. These numbers are just 1, 2, and 3. Are they really related to 7 and 11 and 5? They actually are, and that's the interesting property that leads us to the proof of the identity that phi of a times b equals phi of a times phi of b if the GCD of a and b is 1. In other words, if a and b are coprime. This is what it means for the totient function to be multiplicative. So what we want to do now is understand how these numbers, 5, 7, and 11, are related to these numbers down here. In order to prove that phi of a times b equals phi of a times phi of b, we're going to start by constructing the set of numbers that are relatively prime to ab, between 1 and ab. The size of that set is equal to phi of ab. It's the number of integers coprime to ab. So in the case of AB being 12, we have the set 1, 5, 7, and 11. Those are all the numbers less than or equal to 12, which are coprime to 12. And since there are 4 elements in this set, phi of 12 equals 4. Now we're going to take a look at the right side of the equation. Let's start by considering the sets of numbers that are coprime to 4 and then coprime to 3. Like we saw before, the set of numbers that are coprime to 4 and less than or equal to 4, that's going to be 1 and 3, because these are the numbers that don't have any factors of 2. Over here, when we're looking at phi of 3, the numbers coprime to 3 are 1 and 2. We're going to take these two sets and combine them by turning them into ordered pairs. If you're familiar with set theory, we're doing a Cartesian product, which looks like this, but you don't need to know that to understand what's going on here. So again, we're going to construct a new set that has ordered pairs in it. And the way that we'll do that is we'll take the first number in the ordered pair from the first set. For example, we could use this 1. And then we're going to take the second number in the ordered pair from this set. For example, it could be, again, a 1. We could also have a 1 from the first set and a 2 from the second set. We could also have a 3 from the first set and a 1 from the second set, or a 3 and a 2. So this set right here gives us all of the ordered pairs with the first number from the first set and the second number from the second set. Notice that this set right here has 4 elements. And the reason for that is that each of these sets has 2. So because we're looking at picking a number from each of these sets, there are 2 ways to pick from this set and 2 ways to pick from this set. So the total number of pairs is 2 times 2, 5a times phi of b. So if we can show that for any given number ab, these 2 sets have the same number of elements, that proves that 5ab equals 5a times 5b. Of course, in the case with ab equal to 12, it's pretty obvious that we have 4 elements in the first set and 4 elements in the second set. But how are we going to prove that for a general case? In order to do that, we're going to use something called a bijective function. Now, if you aren't familiar with how this works, I have a video on bijections in the description. The idea is that if we have 2 different sets here, if we can construct a bijection between the 2 sets, meaning we have an exact one-to-one correspondence, where we can map each element in the first set to one element in the second set like this. And there's 1 element for the first set for every 1 element in the second set. This proves that there are the same number of elements in each set. Again, you can check the video in the description where I explain how this works. So we want to try to find a way to go from this first set to this second set that is a bijection. If we can find some function that does that, then we're done. We've proved this theorem. Now I'm going to pick a function that looks like this. For any element x that's in the first set, we're going to take f of x to be the ordered pair x mod a, comma, x mod b. Now this is an ordered pair where each number is x reduced mod one of the numbers a or b. If you aren't familiar with reducing numbers mod n, I have a video on that in the description as well. Let's take a look at how this function works using the example that we have right here. We're looking at phi of 12, and in this case, we're taking a equal to 4 and b equal to 3. So that means that our function here is going to be f of x is equal to x mod 4, since a is 4, and then x mod 3. So let's see how that works for the 4 numbers that we have in our set. First, we're going to look at f of 1. That's going to be 1 mod 4, 1 mod 3. Well, 1 mod 4 is 1, and 1 mod 3 is 1. So that's simple enough. Next, we have f of 5. What is 5 mod 4? Well, we can reduce 5 mod 4. If we subtract 4, we get 5 minus 4 is 1. So 5 mod 4 is 1. Similarly, with 5 mod 3, we subtract 3, so we get 5 minus 3 is 2. So our ordered pair is 1, 2. Next, f of 7. What is 7 mod 4? Well, if we subtract 4, we get 3, so 7 mod 4 is 3. Next, 7 mod 3, notice that 3 actually goes into 7 twice. So we can subtract 3 twice. That's going to be 7 minus 6, which is 1. So 7 mod 3 is 1. And finally, f of 11. What do we get here? With 11 mod 4, we can subtract 8, and that's going to give us 3 as the remainder. So 11 mod 4 is 3. And finally, 11 mod 3, we can subtract 9, and we get 2. This is very interesting. Because notice that the elements that we get here, these 4 outputs, these are exactly what we see in our set. 1, 1, 1, 2, 3, 1, 3, 2. How does that work? How did we get these outputs in such a nice order with this function? Why do we get the exact values from those sets with phi of 4 and phi of 3? In order to understand how this works and where the Chinese remainder theorem comes in, we're going to take a look at coprime numbers. Remember that this first set is related to phi of AB, and that's talking about all of the numbers between 1 and AB that are coprime to AB. So for any number x that's in this first set, we know that it must be coprime to AB by definition, meaning the greatest common divisor of AB and x is equal to 1. One of the properties of coprime numbers is that if AB is coprime to x, then we know that A and B are both also coprime to x. Again, this is in my video on coprime numbers, so you can check the link in the description for that. So because in this first set, all the numbers are coprime to AB, we know that all the numbers are also coprime to A and B. And the important property, which is something I talk about in that video in the description, is that if x is coprime to A, so if the greatest common divisor of x and A is 1, then we know that when we reduce x mod A, it will still be coprime to A. And that comes from the fact that reducing x mod A just involves adding or subtracting multiples of A. And when we do that, it doesn't change whether the number is coprime to A. So we know that x mod A, this first number in the pair, is coprime to A. And similarly, we know that x mod B is coprime to B. Now the reason it's important that x mod A is coprime to A and x mod B is coprime to B comes down to the way that we constructed these sets over here. Remember that this second set is the set of all ordered pairs where the first number is coprime to A and the second number is coprime to B. That's why the number of elements in there is 5A times 5B. So if x mod A is coprime to A and x mod B is coprime to B, what that's telling us is that this ordered pair gives us a pair of numbers where the first number is coprime to A and the second number is coprime to B. Since we reduced them, mod A and mod B, they're also between 1 and A or B. And therefore, they're going to be in this second set. That's telling us that this function always gives us an ordered pair that's in the second set. And that's a very important first step to proving there's a bijection between these sets. So we've proved that this function goes from the first set to the second set. But now we have to prove that it's a bijection. And this is where the Chinese remainder theorem comes in. So let's talk about what the Chinese remainder theorem says. The Chinese remainder theorem says that if we have a system of two congruences, where we have x is congruent to some number k mod A, and x is congruent to some number n mod B, this system of congruences has a solution. And also that the solution is unique, mod A times B. In other words, every solution to this system of congruences must differ by a multiple of AB. Now the condition for the Chinese remainder theorem to be true is that A is coprime to B. Of course that's true in our case because that was one of our assumptions, so we can use this theorem on the situation we're looking at here. In order to do that, we want to rewrite these two congruences in terms of reducing a number mod A and mod B. If x is congruent to k mod A, and we also say that k is between 0 and A, then we can write x congruent to k mod A as x mod A equals k. So this is saying that when we reduce x mod A, we get k as our result. We can do the same thing with this second congruence. If x is congruent to n mod b, and n is between 0 and b, we can say that x mod b equals n. So these two are the same thing. They're both talking about the remainder of x when we divide by b. So the Chinese remainder theorem says that this system of these two congruences has a solution that's unique mod ab. Because these two equations over here are equivalent to this system of congruences, they're describing the same thing, by the Chinese remainder theorem, we know that this system of equations has a solution that's unique mod ab. Now notice, x mod a and x mod b, those are the 2 points, the 2 numbers in the ordered pair of our function. So let's take a step back, remember what we're trying to show, and see how we can use this information to get to that final step. So we just showed that when we're looking at a system of 2 equations, x mod a equals some number k, and x mod b equals some number n, there's always going to be a solution, some number x, that satisfies those 2 equations. Now our goal, when we're trying to prove this totient function identity, is to prove that this function f of x that goes from the set of numbers coprime to ab, and it goes to x mod a comma x mod b. We want to show that that's a bijection with the set of numbers where the first number is coprime to a and the second number is coprime to b. So if we're looking at this situation over here, we know that this first number k, if we want it to be in this set here, k has to be some number that's coprime to a. That's going to make it this first point in the set that we want. And similarly, n has to be some number that's coprime to b, so that it's in this set, like the second points here. So let's see what happens if we say that k is coprime to a and n is coprime to b. So if we set these 2 constraints on the values of k and n, we know that these values k and n have to represent some point in the second set that we're looking at here. So the Chinese remainder theorem tells us that there's some x that gives the correct point in this second set when we do x mod a and x mod b right here. Let's look at some of the properties of that solution x. Remember that if some number k is coprime to a, one of the results that we can draw from that is that the greatest common divisor of k plus some multiple of a with a is also 1. So if we add some multiple of a to the original number k, it's still going to be coprime to a. And that's important to what we're looking at here because we want to look at the properties of x. And k is x mod a. What that means is the way that we get k is by starting with x and adding or subtracting multiples of a until we get a number between 0 and a. That means that the difference between x and k is just a multiple of a, so we can get back to it by adding some integer multiple of a. So if k is coprime to a, then x is also going to be coprime to a. So we know x is coprime to a. By the exact same logic, we can show that x is also coprime to b. And one of the properties of coprime numbers is that if x is coprime to a and x is coprime to b, then we know that x must be coprime to ab. Now this is super important because the first set we're looking at here is the set of all numbers that are coprime to ab, between 0 and ab. So we know that we can find a solution x and that that solution is going to be coprime to ab. But in this first set, we also know that the numbers are between 0 and ab. Can we specify that for our number x? We actually can, Because we know by the Chinese remainder theorem that the solution is unique mod AB. What that's saying is that if we add a multiple of AB, it's still going to be a solution to both of these congruences. And that makes sense because any multiple of AB is going to be congruent to 0, mod A and mod B. So if we get a solution x that's bigger than AB, we can reduce it mod AB and get a number in this set, a number coprime to AB that's between 0 and AB. So how does that relate to our initial question? We're trying to show there's a bijection between these two sets. What we just showed is that for any ordered pair in the second set, for any pair of numbers where the first is coprime to A and the second is coprime to B, we can find a solution in the first set. Now, because there's always a solution, for every output in this second set, there exists at least one input that gives that output, the correct ordered pair. We know that the function mapping x mod A, x mod B, that is a surjection. And the Chinese remainder theorem also says the solution is unique mod AB, which means there's only one number between 0 and AB that solves this system of congruences. What that means is that the function is also an injection. And because of that, we know that this function has to be a bijection. And because the number of elements in the first set is 5AB, and the number of elements in the second set, the number of these ordered pairs, where the first is coprime to A and the second is coprime to B, that is 5A times 5B. We know these two numbers have the same size. 5AB equals 5A times 5B. So that is how we prove that the totient function is multiplicative, meaning that if A and B are coprime, 5A times B equals 5A times 5B. The first thing we do is construct two sets. The first set is the set of all numbers from 0 to AB that are coprime to AB. And the second set is the set of ordered pairs, where the first is coprime to A and the second is coprime to B. We know that we can use the function f of x equals x mod A, x mod B. And that function will give us, from the first set, elements of the second set. Because x mod A is coprime to A, and x mod B is coprime to B, as long as we start from this first set. And by the Chinese remainder theorem, we know that every element in the second set has exactly one input that maps to it, because this system of congruences has exactly one solution mod AB, and that solution is coprime to AB. And therefore, these two sets have the same size, meaning these two numbers are equal. And that gives us a ton more information about one of the most important functions in number theory.